The real challenge in skeletal muscle mechanics is to understand length-tension relationships. If you understand these relationships, then it makes cardiac muscle mechanics much easier. In fact, I said earlier, this section is more or less a prerequisite to heart muscle mechanics. And what I found in the past is those students who do understand these length tension curves find it much easier to put it all together in heart muscle mechanics. So being very careful, and you just really have to understand the main points as I go through here. We're going to take a look at a graph in which we'll have length tension curves. Now the y-axis will be muscle tension, and we're going to measure that tension in grams. Now don't forget there are two types of tension, a passive tension and there is an active tension, and we'll end up with two curves. One is a passive tension curve, the second is an active tension curve, and you have to be able to relate the two curves together and draw firm conclusions. Now the x-axis is muscle length, and we just have it in muscle units here because we don't have to deal with specific lengths. Now to generate these length tension curves in skeletal muscle, we take skeletal muscle out of the body. So we're basically looking at in vitro conditions. Now we'll generate the curve using these in vitro conditions, and then once we're finished, we will relate it to the in vivo situation. Now starting at the very beginning here, then we will just have a skeletal muscle removed from the body hanging from the ceiling. And therefore, because it's simply hanging and there's no preload on this muscle, the passive tension is 0. Now we'll say this is muscle condition A. All I'm going to do is plot muscle condition A as a point on this graph. Now the passive tension is 0. So there'll be no tension in the muscle, but the muscle will have some length. We'll say it has 3 units of length. So this point right on the x-axis represents our starting point. It is simply in vitro muscle, then with no preload on it whatsoever. Now what we're going to do is to examine the consequences of adding some preload. And just for argument's sake then, we'll say we had 1 gram of preload. Now if you add any preload whatsoever, the muscle will get longer and will develop passive tension in proportion to the preload. So this will be a longer muscle, and the passive tension in this muscle will be 1 gram. Now again, we're going to plot this as a point on the graph. The muscle will be longer, and it has 1 gram of passive tension. So according to the way we've drawn this graph then, the muscle length is about 6.5 units, and on the y-axis, if it was drawn accurately, it should have 1 gram of passive tension. Now we're just going to add a third point here to make it easier to draw the curve. If we add additional preload beyond 1 gram, the muscle will get longer again. And we're adding 5 grams of preload, and therefore we will get 5 grams of passive tension. So muscle condition C then is a further elongation of the muscle, and it has greater passive tension. Now we don't have to bother about a specific muscle length, but the muscle length will be out here somewhere. We'll say it's about 8.5 units. And the passive tension is 5 grams, so if you take that point C over to the y-axis, that should be 5 grams. I know this only represents 3 points on this graph, but I know what the curve looks like, and therefore we can sketch in the curve. The curve would look something like this right here. Now this entire curve goes by 2 names. It can be called either the preload curve or the passive tension curve. So it's called either the preload curve or the passive tension curve. And it's simply drawn by adding more preload to the muscle. And the consequence will be, as you move along this curve then, the muscle progressively gets longer and it also develops more passive tension. Now that is the easier curve to deal with. If we go to the next page then, we're going to generate a specific type of contraction in this muscle. We are going to generate an isometric tetanic contraction in this isolated skeletal muscle. Now, an isometric contraction, by definition, is a contraction. Therefore, there will be cross bridges cycling. And we mentioned earlier, by definition, contraction is the continuous cycling of cross bridges. But with this isometric contraction, then there'll be no change in length. In other words, the muscle is not able to shorten. What we have is cross-bridge cycling, but no muscle shortening. And that, by definition, is an isometric contraction. But we're going to generate a specific type. We're going to get a tetanic isometric contraction. Now, we defined tetany earlier as any situation where we saturate the interior with free calcium. So we're going to stimulate the skeletal muscle to the point that we release so much calcium from the sarcoplasmic reticulum that we saturate the interior with free calcium. And as I said earlier, if you saturate the interior with free calcium, all the cross bridges that can cycle will be continuously cycling in this muscle. Now, the important consequence is this statement right here. This is very important for both skeletal and cardiac muscle mechanics. The active tension that you generate during this isometric contraction will be proportional to the number of cross bridges cycling. Now, let me just repeat this in a slightly different format. In an isometric contraction, you saturate the interior with free calcium. Then, in this tetanic isometric contraction, you saturate the interior with free calcium. Every cross bridge will be cycling. But because the muscle cannot shorten, all you develop is active tension on top of the passive tension. So just to repeat that specific point then, because the muscle cannot shorten during this contraction, all you develop is active tension on top of the passive tension. And the amount of active tension you generate is proportional to the number of cross bridges that cycle. The more cross bridges that cycle, the more active tension you will generate. And that is the important basic point to take in to the next figure here, which represents then an additional curve. Now again, being very careful here because this is where it is more difficult to understand what is going on. We're going to use the same three muscle conditions here, but we're going to generate a tetanic isometric contraction. Now in muscle condition A, there was no preload, therefore there was no passive tension in that muscle. Now what we're going to do is we're going to fix the length of this muscle. In other words, we're going to attach an infinite afterload. This afterload is so high or so great that the muscle cannot shorten during contraction. We stimulate this muscle maximally, so we just generate active tension on top of any pre-existing passive tension. Now, I'm making up numbers here just so the curve will come out and look what you see in textbooks. For example, Suppose in this muscle, when we saturate the system with free calcium, we develop an active tension of 2 grams. Now what I'm going to do is I'm simply going to plot this again as a point on the graph. Now the muscle length stays the same. The muscle length is still 3 units. And therefore, at 3 units, I am just going to plot a point that represents 2 grams of active tension. So that point there, brought over to the y-axis, is 2 grams of active tension. In other words, at this muscle length, with all the cross-bridges cycling that can cycle, I will develop 2 grams of active tension. Now, muscle condition B was pre-stretched because we added 1 gram of preload and we developed 1 gram of passive tension. Now remember, not only do we pre-stretch the muscle, we also pre-stretch the sarcomere. And the importance of this will be apparent later. Now, just for argument's sake, we'll say this pre-stretch caused 4 grams of active tension to develop in that muscle. And again, I'm going to plot it as a single point. Now, the carryover from the previous graph is not perfect, but this supposedly is the original length of muscle B, about 6.5 units. The preload caused 1 gram of active tension, and the isometric tetanic contraction generated 4 grams of active tension. So we start from the origin again, and we simply go up 4 grams, and this brought over here would represent the 4 grams of active tension. Now, muscle condition C represented a greater pre-stretch of the muscle and sarcomere because we added 5 grams of preload and got 5 grams of passive tension. Now again, just for argument's sake here, because I want the curve to come out to a reasonable shape, when we stimulate this muscle to contract, we got 3 grams of active tension. Now again, we're starting at the same original muscle length. Now it doesn't transpose perfectly from the previous page, but this will say is our 8.5 units of original length here. The preload caused us to generate 5 grams of passive tension, but during contraction, we only had 3 grams of active tension, and therefore we plot a point in the same vertical line that represents 3 grams. This point brought over to the y-axis would represent that 3 grams of active tension. Now again here, this is not a complete curve. We only have 3 points, but I know what the curve looks like. It is a bell-shaped curve. It will have an ascending limb, it has a peak point, and it has a descending limb. Now this dashed line representing the curve we just drew is simply telling you one thing. It tells you the amount of active tension you generate in the muscle then at a particular pre-stretch point then. So all this is telling you is active tension, and don't forget this active tension is proportional to the number of cross bridges cycling. Now as I said, you have to correlate the 2 curves here, and this should be your interpretation. If we start with no pre-stretch of the muscle, no pre-stretch of the sarcomere, we only generate a small amount of active tension during contraction. On the other hand, if we pre-stretch the muscle, what we find is we generate more active tension during contraction. If we pre-stretch the muscle to point B, we get the greatest amount of active tension. So at this point here, we are generating the greatest amount of active tension. We have the greatest number of cross bridges cycling. This is where the muscle is providing maximum performance during contraction. Now they won't test this terminology on step 1, but this point where we get maximum performance out of this muscle is called LO. Now, LO is actually the length of the muscle, but LO is the length, the pre-length of the muscle that provides maximum performance. So the muscle is performing maximally here, so it must have been pre-stretched to LO. Now, LO, as I said, is read as a muscle length. So this point brought down to B is the same muscle length. So B represents LO, but you're actually reading LO off the x-axis. Now again, just approximating. The LO here is about 6.75 unit lengths then in this muscle. So if you pre-stretch the muscle to this length here, it performs maximally. Now continuing with this graph here, if you pre-stretch the muscle beyond B, then what happens? Well, we get less active tension for some reason. So if we stretch the muscle beyond LO, the amount of active tension we generate decreases. Now when we get to this point then, we have pre-stretched the muscle to the point there is no active tension. Now this is a summary of what we've gone through so far. Now if there's no pre-stretch of the muscle then, we only get a modest number of cross bridges cycling, so we get a modest performance, a modest amount of active tension. On the other hand, as we pre-stretch the muscle towards LO, we get an increased performance. More cross bridges are cycling. If we pre-stretch the muscle exactly to LO, we get the greatest performance out of that muscle, which means we have the greatest number of cross bridges cycling. But if we pre-stretch the muscle beyond LO, for some reason, fewer cross bridges are cycling, and we get a diminished performance as expressed by a decrease in active tension. Now, this is what you have to understand for sure. The number of cross bridges cycling depends upon the arrangement of the thin and thick filaments. It is the alignment of the thin and thick filaments that determines the number of cross bridges cycling. If you pre-stretch the muscle to LO, you have the perfect alignment of the actin and myosin, and therefore every cross bridge can cycle. Now this is illustrated at the bottom of this figure here. This is muscle condition B. Muscle condition B has been pre-stretched to LO. You have the perfect alignment of the actin and myosin, and therefore every cross bridge can cycle. So this is a sarcomere that you would see in a muscle that is pre-stretched to LO. Now, if you go beyond LO then, what you have to be able to imagine is the actin and myosin are pulled apart. There is a decrease in the overlap between the actin and myosin. If there's a decrease in the overlap between the actin and myosin, fewer cross bridges will cycle and you develop less active tension. And this is illustrated then again at the bottom of this figure here. This is a sarcomere that has been pre-stretched beyond LO. And because it is beyond LO, notice the cross bridges in the center part of the thick filament cannot cycle with the thin filaments then. So these cross bridges are not contributing to active tension. Because fewer cross bridges can cycle between the actin and myosin, less active tension is generated. Now going back to LO here, our ideal pre-length or pre-stretch. If I take off the pre-stretch that we produced to generate LO, then this sarcomere will get shorter. Now this is harder to imagine, but if you take off the pre-stretch from LO, then you get a squashed sarcomere. What we're showing here is the thin filaments hitting one another. They get distorted, and therefore you can't cycle as many cross bridges. If it becomes really short, and we're not showing this here, the thick filament can actually hit the Z lines and curl around. The bottom line for all of this is simply the following. If there is no pre-stretch of the skeletal muscle, if there's no preload or pre-stretch, you just have to accept you have a squashed sarcomere. And in the squashed sarcomere, you do not have the perfect alignment of the actin and myosin, and not all of the cross bridges can cycle. If you add pre-stretch to the muscle, you pre-stretch the sarcomere. This improves the alignment of the actin and myosin. More cross bridges will cycle, and you get a greater active tension. If you pre-stretch the sarcomere to LO, you have the perfect alignment of the actin and myosin. All cross bridges can cycle, and if you saturate the system with free calcium, you get maximum performance out of this muscle. However, if you pre-stretch the muscle beyond LO, you decrease the overlap between the actin and myosin, fewer cross bridges can cycle, and less performance. That is the important aspect of this graph here. Now, just to add some details and reiterate a few points, going back to muscle condition A, and this is a small point, we had 0 passive tension, we generated 2 grams of active tension, and therefore the total tension during contraction was 4 grams. With muscle condition B then, we had 1 gram of passive tension, 4 grams of active tension, therefore the total tension during contraction is 5 grams. Now in muscle condition C, we had 5 grams of passive tension, 3 grams of active tension, and therefore the total tension is 8 grams. Now that's a detail that's probably not important for step 1. Now on the next figure here, what we have is a graph that is more appropriate for a textbook that combines everything together here. Now this is the same graph that we just generated step by step. The y-axis is muscle tension. One curve provides passive tension, a second curve provides active tension, and the third curve is the total tension during stimulation. The x-axis again is muscle length. Now this is the ideal pre-length the sarcomere and the muscle has to be at to generate maximum performance. Now looking at individual curves, this curve here is the passive tension or the preload curve. This bell-shaped curve is the active tension curve. Now we said at the peak of the active tension curve, we have maximum performance, and therefore this muscle must have been stretched to LO. So this is that pre-length LO. It also represents this point here and this point on the x-axis. It's actually read as a length on the x-axis. Now finally here, with this graph, what we've done here is we've simply reproduced the active tension curve, and we show what the sarcomeres would look like at different points on this curve. Now this is the bell-shaped active tension curve, and therefore this point must correspond to LO, which is maximum performance. Now what we're showing here is a sarcomere that has been pre-stretched to LO. Sarcomere B here is at LO, and the maximum number of cross bridges can cycle. On the other hand, suppose we go beyond LO, we overstretch the sarcomere. This is an overstretched sarcomere. If we take it to the ultimate state then, we overstretch the sarcomere to the point we get 0 active tension. At this sarcomere length here, when we stimulate the muscle, we generate zero active tension because we have now stretched the sarcomere to the point there is no overlap between the actin and myosin. This is basically a useless sarcomere. It's a totally useless sarcomere. It cannot generate active tension. It cannot shorten during contraction. Now, going the other way, and this is illustrated better here than in the previous page. If you take off then some pre-stretch, one of the first things you'll see is the actin filaments will hit one another, they become distorted, and fewer cross bridges can cycle. Now, if you took this all the way to the point where there is no pre-stretch, now we're not showing it here, but the thick filaments would hit the Z-lines and they would curl. And because they curl, again you have a distortion between the thick and thin filaments, fewer cross bridges can cycle. So the bottom line point is, if you pre-stretch 2LO, you get maximum performance out of that muscle. Now, what we've been talking about here is skeletal muscle in vitro. Now, suppose we try and relate this to the in vivo situation, and very little of this is in your handout. Now, suppose this is my muscle in vivo that is connected to these 2 points right here. So my skeletal muscle is in vivo connected to these 2 fixed points. And I'm purposely using this example here. When I contract this muscle, I want maximum performance out of this muscle if required. Therefore, in order to maximize performance, what length must this muscle be at under resting conditions? And the obvious conclusion is this muscle must be at LO. And that is the important point. Skeletal muscle in vivo is pre-stretched exactly to LO. So if you stimulate skeletal muscle in vivo, you will obtain maximum performance out of that muscle. So just to repeat that, all skeletal muscle in vivo, relaxed resting muscle, is pre-stretched very close to LO. So when you stimulate that muscle maximally, you will get maximum performance. Now, this is one way boards can test that particular point. This is a relaxed resting muscle. Now, if I cut the tendons to this muscle, what is going to happen to muscle length? Well, you should conclude there should be a passive shortening of the muscle because you eliminated that pre-stretch 2LO. So if you sever the tendons of a muscle in vivo, you should realize there will be a passive constriction of that muscle. You've eliminated that pre-stretch 2LO. Now, another way of testing this is to ask you, if you cut the tendons to a skeletal muscle in vivo and you want to reattach those tendons, what should you do before you reattach the tendons? And you should conclude you must pre-stretch that muscle 2LO. If you don't pre-stretch the muscle 2LO then before you reattach the tendons, the muscle will never perform maximally again. And that is just one way of testing the important aspects in vivo then. Now, that was an important section in skeletal muscle mechanics. Now, we do have to say a few things here about an isotonic contraction, but the details are not too important. I'll try and emphasize the main points that are relevant to step 1. Now, we'll start off by defining an isotonic contraction. Now, an isotonic contraction, because it is a contraction, means the cross bridges will be cycling. But in this case, the load is lifted or moved. In other words, if you stimulate a muscle to contract and the muscle does not shorten, you have an isometric contraction. If you stimulate a muscle to contract and the muscle does shorten, It's an isotonic contraction. Now, we're going to the in vivo situation here just to make a single point. Suppose this muscle in vivo has been pre-stretched to LO, and that pre-stretch caused a tension or force in the muscle of 100 grams. But when this muscle contracts, it must lift this weight. And to lift this weight, you need a total force of 800 grams. Therefore then, you should realize when this muscle is stimulated to contract, it will not shorten immediately because it must build up to a force of 900 grams. And to build up to a total force of 900 then, you should realize you will develop 800 grams of active tension. So in the initial stages of contraction then, you will get cross-bridge cycling, no shortening of the muscle, but that cycling will build active tension on top of the passive tension. And when the total reaches 900 grams, the muscle will shorten. Now you can't think this through. This was determined experimentally. Now the only reason we put this page in is to emphasize this point. And that is, most of the energy consumed during the previous contraction was utilized to develop active tension. The bottom line point is, the development of active tension is a very energy-demanding process. It requires a lot of ATP compared to the amount of ATP during active shortening. So just to repeat that then, during this contraction with the muscle in vivo, most of the energy was consumed initially in the contraction by developing active tension. Once the muscle started to shorten, very little ATP was consumed. Now, we can relate that to cardiac muscle, and I'll reemphasize it later. During the contraction of ventricular cardiac muscle, during isovolumetric contraction, you are developing active tension in that muscle, and that consumes a huge amount of energy. When that muscle begins to shorten, when you begin to eject that blood into the aorta, much less energy is consumed. So during the cardiac cycle then, and again we'll reemphasize this later, most of the energy is consumed by ventricular muscle in the development of pressure in that ventricle. The pressurizing that blood is a very energy-demanding process. Now that is the reason we put this figure on the handout. Now it is not high yield, but every once in a while they have tested, and I think in skeletal muscle, the relationship between the velocity of shortening and the load on the muscle. And by load, we mean afterload. We are again relating this to the in vivo situation. So we're just going to look at the relationship between how fast the muscle shortens and the load the muscle has to lift. Now, they have tested this relationship by showing this graph here. This graph plots velocity versus the load the muscle is trying to lift. Now, we'll start off by examining muscle condition A. In muscle condition A, we will look first where there is no afterload on that muscle. If there's no afterload on that muscle, we will get the greatest velocity of shortening. Now, they probably won't test this term, but this point is called V max. This is the greatest velocity you can generate in this muscle. The greatest velocity of shortening is when there is no load on the muscle. Now, if you add afterload to the muscle, what happens is the velocity decreases. It's an inverse relationship. The greater the afterload, then the smaller the velocity contraction. When you get to this point here then, there is no velocity. You've gone to an isometric contraction, but the muscle is developing maximum force. Now, if they tested anything in reference to this graph, they would test what determines this point right here. That is, what determines the maximum velocity of contraction. And you have to remember, this is determined by the muscle's ATPase activity, not ATP. It is determined by the muscle's ATPase activity. The greater the ATPase activity, the faster the muscle shortens. We'll reiterate this point, but it is the ATPase activity that determines a fast versus a slow muscle. Now, it is possible they could test what characteristic determines this point right here. In other words, what characteristic of muscle determines the maximum force you can generate. Now, the maximum force is determined by muscle mass. The greater the mass, the greater the force that muscle can generate. Now, that is not going to be tested as often as the other point, but we put that in just to be complete. Now, to make sure there's no misunderstanding here, we will compare muscle A with muscle B. Now, with muscle B, it starts higher on the y-axis. That means it has a greater Vmax or velocity at no load. That means muscle B is a faster muscle than A. Muscle B also crosses the x-axis further away from the origin. That means muscle B generates more force. That means it's a more massive muscle. So overall, muscle B is a faster, larger muscle than muscle A. Now, what we've done here is we've actually divided our muscle into the two main types in vivo. Muscle A is a red muscle, whereas muscle B is a white muscle. Now, every once in a while, step one will compare white skeletal muscle with red skeletal muscle. Now, white skeletal muscle then has specific characteristics. If you want a good example of a white muscle, that would represent the leg muscles of a sprinter. White muscle tends to be large muscle that is utilized short term. Now, another example of white muscle they could test on the exam would be the ocular muscles of the eye. Now, these are not large muscles, but they're very fast muscle. Ocular muscle is white muscle, and therefore it is very fast. Now, the first two characteristics listed here are those that we talked about on the previous graph. White muscle is a large muscle. It has high ATPase activity, therefore it's a fast muscle. Now, an additional characteristic is that white muscle has a high capacity for anaerobic glycolysis. Now, anaerobic glycolysis is very fast at resynthesizing ATP, but it is very inefficient. And therefore, it is appropriate, though, for large muscles where you use them just short term. Obviously, white muscle does not have myoglobin then, because it is white muscle. Now, red muscle is at the opposite end of the spectrum here. And again, a perfect example here would be postural muscle. So if you want a good example of a red muscle in vivo, it would be postural muscle. It is generally a smaller muscle that is utilized long term. Red muscle is considered endurance muscle. Now, the first two characteristics, again, are what we shown on the previous graph. Red muscle is a smaller muscle. It has lower ATPase activity. Therefore, it's a slower muscle. In addition, you should realize red muscle has a very high capacity for aerobic metabolism. Now, aerobic metabolism is slower than anaerobic glycolysis, but it is much more efficient. And of course, red muscle contains myoglobin. Now you probably should remember that myoglobin not only stores oxygen, it tends to facilitate the transfer of oxygen to the mitochondrion. So the presence of myoglobin then speeds up the transfer of oxygen to the myoglobin. Now finally, in this section here on skeletal muscle, we tried to summarize the histological features of skeletal, cardiac, and smooth muscle. Every once in a while, and again, it's not a high-yield aspect of the exam, but every once in a while, they will compare skeletal, cardiac, and smooth muscle. You have to know what they have in common, but more importantly, you have to know their differences. Now, I am going to only emphasize the really important points here. First of all, skeletal muscle is striated muscle. It is striated muscle because the actin and myosin are organized into sarcomeres. Cardiac muscle is also striated muscle because its actin is also organized to form sarcomeres. Now in smooth muscle, then it is described as non-striated because the actin and myosin are not organized into sarcomeres. Now the second aspect here is reasonably important. In skeletal muscle then, the sarcolemma lacks junctional complexes between fibers. That simply means the individual fibers of skeletal muscle are not connected electrically. That means the action potential does not spread from cell to cell. Therefore, to activate skeletal muscles then, each fiber must be separately innervated. So because the action potential cannot spread from cell to cell, then each muscle cell, each muscle fiber must be separately innervated in skeletal muscle. However, cardiac muscle and smooth muscle have junctional complexes between the fibers, including gap junctions. Now, gap junctions, as we said earlier, are regions of low electrical resistance. And when you have gap junctions between fibers, then the action potential can move from cell to cell. Therefore, cardiac and smooth muscle represent an electrical syncytium. And that is very different from skeletal muscle. Now, the next aspect, not real important but worth mentioning, as we said earlier, in skeletal muscle, it is troponin that binds the calcium to initiate contraction. In cardiac muscle, you also utilize troponin, but in smooth muscle, you utilize calmodulin. It's worth remembering that smooth muscle utilizes calmodulin instead of troponin. Now, the last important point is this line here, and we already made this point. That is, high ATPase activity represents a fast muscle, and you should realize that skeletal muscle is the fastest muscle in the body. Skeletal muscle is extremely fast because it has high ATPase activity. Cardiac muscle is intermediate, and smooth muscle has low ATPase activity. Therefore, smooth muscle is considered a slow muscle. Now, the last line is so low yield, it's not really even worth mentioning. Now, there is one other aspect here that I did mention earlier, and that is in skeletal muscle then, the surface membrane lacks calcium channels. Very big point. Therefore, extracellular calcium is not involved in skeletal muscle contraction. However, both cardiac and smooth muscle have voltage-gated channels in the surface membrane, and as we'll mention later, in both cardiac and smooth muscle, both intracellular stored calcium and extracellular calcium will be involved in muscle contraction. Now that finishes off the skeletal muscle section. And what we've tried to do here is to emphasize the main points board will test, and notice most of those points can also be applied to cardiac muscle. Then you should go through and understand this information before you go to the cardiac muscle section.